Good morning. I think we're about ready to start. Okay. Hi, everyone. So we're going to continue on with class today. Let me see. Okay. Good. Now, so we're going to continue with radiation physics today. Just a couple of things. So assignment 1, I graded and returned to you, but I am still waiting for one from one of the students, so I haven't posted the solution yet. So if you're looking for the solution, you won't find it yet, but soon. We will discuss the solution next time on Thursday. The other thing is the office hours poll. And it looks like the time that I guess the maximum number of people are available. Naturally, we couldn't find a time that everyone is available. But the time at which we are maximized is Friday afternoon. So what I'm going to plan to do, I think, is set kind of a standing reserve time Fridays at 1 p.m. And I will make sure I'm available at that time, probably for the next couple of weeks at least. I will just go ahead and get on the Zoom at that time, and I'm not going to wait a real long time. If nobody shows up, I'll go off. If you know you're going to have questions and you know you're going to tune in, it'd be good to send me an email, give me a heads up on that, so that I'm expecting you. To go along with that, I'm going to probably start trying to schedule assignments so they are done, so they are due after that. So, maybe Mondays, and that's going to that might change some things on the schedule a little bit. But that way, hopefully by Friday, if there's a assignment due at the beginning of the following week, then by Friday, hopefully you've started working on it, and we can address questions that you have at that point. Also, again, if that's not a good time for you, or you have something that doesn't fit that schedule, just drop me an email. We can schedule another time. Since the Zoom meeting is basically a standing meeting that can be accessed at any time, we just use the same access numbers and passwords as is normally used for the course. Okay. Does anybody have any questions on that? Okay, so because of that, expect assignment 2, to be due past the end of next week, so the beginning of the following week, basically, is what I think that's how we'll have to do it. That's pushing it out a little farther than I might like, but I think that's what we're going to do. So, okay, if there are no questions on that, then we're going to continue with our radiation physics discussion. And so, kind of to set where we were, the kind of the first most important thing is to understand that we talk about 2 different kinds of radiation. And when we say radiation, we're basically talking about energy that travels, in a sense, from one place to another. It can be particles, it could be electromagnetic. Okay, and so basically, we could have waves, we could have things with mass that fit into this. Now, What we're kind of in the middle of is kind of talking about some of the considerations about these different kinds of radiation and how they interact with matter, because that's the whole basis of imaging, right? Essentially, we're going to be firing radiation or applying radiation to the subject and measuring how they respond. That's the basis of what we're doing in imaging. So, one of the main things that we have to be able to deal with is, okay, how do these things interact with matter? Okay, so we talked about the particulate form of radiation and how it interacts with matter. But most of the particles don't interact in ways that are helpful to us from an imaging standpoint. They might interact with tissue in the body in ways that are helpful from a therapy standpoint. In other words, they do damage, right? And so you might, the basis of radiotherapy is to do damage to the malignant tissues and spare the benign tissues as much as possible. And so there are certain strategies that use some of these heavier particles for radiotherapy. But for the most part, we're dealing with the betas, the electron and positron particles, which are much lighter particles, and are used in sort of ways. But in general, we aren't having them interact directly with tissue either in order to do our imaging, although you might say that about PET imaging. So we'll see how that goes, right? And the basic idea, of course, is how electrons, but actually any of the particles really, losing energy to a medium, basically they can cause ionization, they can cause heating in the medium, or they may create X-rays, right? And so basically those are the three ways to kind of balance the energy equation with respect to particles. They might ionize atoms, they might just cause frictional or vibrational heating, and they may generate X-rays, other forms of radiation. And so we discussed, the difference between characteristic and Bremsstrahlung. And we kind of, I do want to revisit this portion because this is one of the things that people have a little bit of trouble with, okay? And it's applying relativity in understanding the energy of an electron. Because, back in physics and doing classical mechanics, basically a moving mass has kinetic energy 1/2 mv squared, where m is the mass, v is the velocity. However, the problem is that is more or less an approximation that works as long as your velocity is a lot less than the speed of light, which, right, most things moving through the environment in a classical mechanics sense, that works fine. But when we start talking about these very small particles going at very high velocities, fractions of speed of light, then we have to kind of rethink this a bit. And it comes down to a way of looking at it. Again, this is happening on a quantum level, so it's not necessarily what's going on, but it makes the equations work, and it's a way of thinking about it, is the fact that as the velocity approaches speed of light, or the order of the speed of light, then there is a change to the mass. The effective mass, the relativistic mass of the particle actually increases effectively, and that gets plugged into the classic E equals mc squared equation. Okay. So if we step back and say, okay, you know, to answer these questions, the rest energy of an electron, the rest energy of a proton, velocity is 0, so the mass is, the relativistic mass is equal to the rest mass, and so we plug in E equals m naught, c squared for that, and if, you know, c is a constant, so that's fine. If we did that, given the mass for the electron, we would find 511 keV, which is an important number that we will refer to over and over again. The proton, I didn't calculate that. I think that's on the homework. But again, it's just plugging into the equation. So if they're not moving, that's fine. That's easy. There's no modification to the mass at all. But let me interject a slide here. Okay, now, so let's say, as an example, oops, got to get my writing in order, sorry about that. Let's say we're going to accelerate an electron. Okay. And let's say I was going to accelerate that electron to 1/10 of the speed of light. All right. So the first thing I need to know is its relativistic mass. And the relativistic mass of the particle, given the previous equation, is going to go like this. And that was the velocity over c quantity squared. Okay, well, then we're going to get, if this is 0.1 c, then the c's cancel out. We don't actually have to plug that into the equation. And so this ratio becomes 0.1, and therefore you just kind of go through and calculate through that, and you will find that that becomes 1.005 m naught. I'm going to keep it just in terms of the, you know, relative to the rest mass of the electron. Okay. Okay. So its mass has to increase a tiny bit, right? 0.5% basically. All right. So if that happens, then we calculate his total energy. And the total energy is going to be its rest energy plus the kinetic energy, okay? And that was given as equals mc squared, but notice that that m is the m we calculated up here, okay? So given that, we would find that this becomes, I've already calculated these out, 513 about point, we'll say 57 keV. Okay, and just as a note about units, we are, because in this field, this is how, you know, these are the units that are most commonly used. We are exclusively talking about energy in terms of keV, kilo electron volts, and there's a ratio that, you know, there's a factor that relates that to joules. But this is a measure of energy. Okay. All right. So that's the total energy. In which case, the kinetic energy is going to be E sub k is going to be the total energy minus the, what we'll call the potential energy, or the rest mass energy. In other words, easier, and when we talk about the rest mass energy, that's basically the energy in the particle that we would obtain if we converted it entirely to energy, mass to energy conversion, which does happen, and we'll see examples of that, okay? But you could say that's the mass potential energy or the rest energy, or that's kind of inherent in the particle just having mass and not moving, okay? And E naught for a electron, again, 511 keV, so that leaves us with kinetic energy of 2.57 keV is what it would take to accelerate an electron to 1/10 of the speed of light. Okay. Any questions on that? Okay.
I have a question.
Yeah, go ahead.
To solve for total energy, so we know the rest mass, right?
Yes.
Okay. Is that, where do we look up those values?
Virtually anywhere they're on Wikipedia.
Okay.
Yeah, I mean, again, those as physical constants, those are easy to find. Obviously, for our purposes, and they're calculated to 10, maybe 20 significant digits or whatever. For our purposes, not necessary, right? Just a few significant digits is all we really need. Okay? And in fact, I've approximated some stuff here because I just the E naught for the electron is 511 point something. I don't even know what it is, but so I've kind of approximated here too. Reasonable approximations are fine, but it's important to keep units straight, right? This is one of the things you'll find in working with a lot of these physical things, and that was true back in physics also, that keeping your units straight was important. Just by way of comparison, quickly, if we did the same thing for half the speed of light, okay, we would get 1.155 times m naught. So it's actually, the mass has increased now by 16%. We would get, what have I got here, 590.1 keV, and the kinetic energy would be 79.1 keV, and this actually is right in X-ray range, at least in some applications. Sometimes we go higher than that. So, the bottom line here is that this is in the ballpark of at least some of the electrons when in an X-ray tube have to be accelerated to 80 keV by putting 80,000 volts across it. The velocity of those electrons as they're traveling in the X-ray tube is going to be on the order of about half the speed of light. Okay. And as I mentioned last time, basically, as you try to get closer and closer to the speed of light, the mass goes up faster and faster and faster, which means it's going to take more and more and more energy to get there, which means, to the point of, okay, if I really wanted to accelerate that electron, well, to the speed of light, theoretically, its mass would become infinite, and it would require an infinite amount of energy, right? So we can only asymptotically approach the speed of light with masses, okay, by injecting more and more and more energy into them, but with a lot of diminishing returns. Okay, and so that kind of takes you back to the basic principle that you've heard that, okay, things can't travel faster than the speed of light. Well, this is at least a way of looking at that. Masses cannot travel faster than the speed of light for this reason. Okay, any other questions on that? This is one of the things that I know people have a little trouble with from year to year. So I wanted to spend a little bit of extra time on it and illustrate that a little bit better. Because a lot of people jump back to classical mechanics and 1/2 mv squared, but you'd find that these numbers don't match up at all with them. Okay, and again, maybe at 0.1c, 1/2 mv squared might be close to this because it's a relatively small effect, but as the effect becomes more significant, then it starts to fall apart. Okay, and this will be in the annotated notes that I put up. Okay, so that was kind of going back to some things that we looked at before. Again, you can find those constants you need. A lot of equations are going to be using Planck's constant. Okay, so just be aware of that guy, and the fact that, again, energy, frequency, and wavelength are all kind of saying the same thing in different ways. Okay, so a particular frequency of an electromagnetic wave has a specific wavelength and a specific energy associated with it. Okay. And where we left off was in this discussion of nuclear transitions and radionuclides, right? And the point here, of course, is that we use, one way we produce radiation is through an X-ray tube, and we'll talk about how that's done. But another way we produce useful radiation is by using radioactive materials. And so we kind of left off with the fact that, well, there's a couple of different terms for the kinds of transitions that you might do. The idea being that if something decays from a radioactive material into a inert material, it has to give off energy, and there are different ways that it can do that. And this, of course, was kind of illustrating how we go from one type to another. Okay, so I want to start with doing a little bit more there because there's a little more to talk about here. We kind of left off saying, okay, well, we got a couple of examples, real examples of that. Isomers where 99 metastable technetium actually decays to stable 99 technetium in a way that actually doesn't change the number of particles, so they're both technetium and they're both 99. But basically, you can think of it as a change of the packing of the particles from a less stable energetic state to a more stable ground state. Okay, and so it has to give off that energy. It gives it off in the form of a photon. There was an example here of this is a transition that's done. Iodine-131 is actually used for radiation therapy, and so it transitions from a less stable state to a xenon form by essentially, well, in effect, it exchanges a neutron for a proton, but there's a little bit more to it than that, as we'll see in a second. And then this example, actually, I just wanted to clarify, wasn't an example of a transition that actually happened. So this is iodine-131, this is iodine-131. These are just isotopes. They're both iodine. They have different numbers of neutrons, but actually it doesn't, iodine-131 doesn't go from iodine-131 to iodine-127. It's much more favorable for it to do this transition, right? So this is just demonstrating, okay, these are two different isotopes of iodine with different behaviors. Okay. So the transitions that, occur that matter in medicine are essentially going to be the isobaric, which is a term we don't hear all that much. I mean, we use the term isotopes all the time in kind of throwing these around, but the more specific term would probably be isobars, but you don't really hear this used that much. And so the things that can happen, and so this basically means, okay, we're changing around neutrons and protons. in the nucleus in these materials. And so depending on which way you go, remember that we have to have, in all of these kind of transitions, we have to conserve some things, right? In other words, we have to conserve mass in these equations, we have to conserve energy, and we have to conserve charge. Okay, and so with all of these transitions, all of those things end up having to be conserved. And so, for example, some materials that are used will emit a beta minus, which is an electron. Okay? And so the kind of way to balance all of those things through this equation is to say, okay, well, a neutron is a neutral charge, so, and it's going to essentially convert to a proton, positive charge, an electron, negative charge, so those balance out and conserve charge for us. And then our little friend, the neutrino, which physicists probably wouldn't like me to say this, but basically is the fudge factor that balances everything out. It has a tiny bit of mass, it has no charge. Because it has a tiny bit of mass, it has a tiny bit of energy. Okay, they do exist, and they've proven that they exist, and people have actually measured them, but they pass through everything and they don't really matter to us. So for our purposes, you know, that's just there to kind of balance things out, and it's not really going to affect anything that we do. So for our purposes, effectively, we are converting from a neutron to a proton and an electron, and the electron is given off. Okay. The reverse can happen, right? This is a beta plus, which means a positron, and so proton, +1 charge, converts to a neutron, and then the positron accounts for the charge balancing, and then our little friend, the neutrino, helps to balance things out. Okay. So again, for our purposes, proton becomes neutron, gives off a positron. Another one that can happen that's a little bit similar, okay, it's just that it balances a little bit differently, is the idea of electron capture. And so this is, again, effectively converting proton to neutron, but we're not really giving off the positron. In this case, we're using an electron on the other side to effectively cancel out the charge of the proton, give us a neutron, and then energy is balanced by the gamma that's given off, a gamma photon. Okay. So some things do this. And so as a result, right, here we're giving off electrons, here we're giving off positrons, here we're giving off gamma photons. And in fact, I think I'll just write that here, right? So these are materials that give off electrons, these are materials that give off positrons. These are materials that give off gamma photons. Okay, and then there, in addition to those, are the isomeric transitions, which again is like this guy, right? We just have a kind of a state of slightly less stable, usually called metastable state, because it can stay in that for a long time, but eventually it's got to give off that energy. And so again, in order to balance the energy, we're not converting any particles here, we're not converting neutrons, protons, etc. It's just got to give off energy. And so a gamma emission, well, that's more or less stating what it is, right? That's giving off a gamma photon. And then the other possibility is what's called internal conversion, where effective, I mean, you could think of it as giving off a gamma photon, but it actually interacts with shell electrons to the point that the it kicks out a shell electron in order to give off the energy. And so this, we're giving off an electron. So these materials are giving off electrons. Okay. So those are the things that we're dealing with, right? Again, some of them are particles, some of them are materials giving off particles, some of them are materials giving off electromagnetic radiation. This is a not great illustration of some of those possibilities, okay? The point being that everything needs to find its way to a stable state eventually, okay? And so, you know, one possible transition, neutron to proton ratio, right? If that's high, then it tends to want to you know, give off electrons, or you can think of it as if the neutron to proton ratio is high, then it tends to want to convert neutrons to protons and reduce that ratio. And so in doing that, it gives off an electron. And the opposite is true here, right? Here it's trying to increase that ratio. Here it's trying to decrease the ratio. We had two possible transitions for the low neutron to positron, neutron to proton, I keep doing that, ratio. These two, beta emission, positron emission, and the electron capture. So again, and then the other possibility, although this is not great because it implies that, oh, then this happens. No, that's not true. These maybe should go down to here. But this is what we actually, I can draw that, right? We should be kind of thinking of it more this way. And so I should probably correct this thing. However, it's also true that a lot of radioactive materials go through more than one of these transitions, okay, in order to get to the ground state. And so that's the other thing you should be aware of, is that the ones we tend to use are ones that have single transmissions or very dominant transmission paths in order from going to the unstable to the stable state. But there's a lot of radioactive materials that are, let's say, messier, that might do some of this and some of that and some of this, you know, in order to get down to the ground state. And so as a result, they give off a lot of different things. And that's usually, those are usually the ones we don't want to use. So we might not hear about them as much, but you should be aware of that. There are books with tables and tables of all of the possible isotope transitions and the relative percentages of them all, okay? Because even things that are pretty clean and, you know, mostly give off predictable things might have some other transitions that happen that are much less less stable, or, well, I shouldn't say stable, less likely, but they do happen, you know, when you have a big bulk of material. So, okay. All right. And then the last concept to talk about with radioactive material is radioactivity, and essentially what's happening there. So you kind of do have to think about this in a, let's say, probabilistic sense, because if you're looking at it from the perspective of one particular atom, I have this one unstable atom from this one material, there's no way to know, and he doesn't really communicate with his buddies in the bulk of material, the other atoms in the bulk of material. There's no way to know when he's going to go. In other words, emit his electron or positron or photon and convert from his unstable state to his stable state. It's just that when you have a bulk of material, right, there is because of the essentially how unstable the material is, right, the physics of that, they're, you know, some of the atoms are going to go at certain times and others are going to go at other times. And in the bulk of material, given that the kind of fundamental probability associated with that particular material, things are going to tend to happen at a certain rate. And that's more or less a physical constant for that particular material. Okay. So if you think about a bulk of material as a whole bunch of radioactive nuclei, right, radioactive atoms, then a certain, in a given time interval, a certain number of them are going to decay from unstable to stable. Okay, and that's more or less given by this different, you know, what is a very simple differential equation, right? The activity is basically the rate of change of nuclei per unit time. And conceptually then, if you think about, okay, I've got a bulk of radioactive material and a certain amount, certain percentage of those are going to change in a certain amount of time, then over time, all of the atoms in that material are going to change, but it's going to go at a, you know, I'm going to observe fewer and fewer photons as with time, because more and more of the atoms have converted from unstable to stable, and eventually they're all going to be stable state, right? And that's the idea of radioactive decay. Just conceptually in this question, right, if you think about, okay, I have two different emitting radionuclides and they have the same radioactivity, where the radioactivity is defined as the number of atoms converting. The question is, do they give the same photon flux? Well, first of all, we have to assume that they're giving off photons, right? Because not all of them do. Some of them give off things that are not photons. But the other thing is, some nuclear decay schemes may give off more than one photon. So you can't necessarily say this is true, right? In other words, I could have two masses of radionuclides with the same radioactivity, meaning the same percentage of nuclei are converting in a given amount of time, but one gives off one photon per conversion and one gives off two photons per conversion, right? We're going to see more photon flux from the second. That's just a conceptual thing just to be aware of. Okay. That this refers to nuclei changing, not necessarily what's given off. Okay. Units of radioactivity, again, units are important here. And the two units of radioactivity are the Curie and the becquerel, obviously named for people who are important in this field. The Curie, so these are both related, these are both in terms of disintegrations per second. Okay, in other words, how many nuclei are converting per second. The Curie is a lot of material or a lot of activity, right? 3.7 times 10 to the 10th per second. And becquerel is 1 disintegration per second. The Curie is the older unit, but still almost, it's funny. I mean, if you go down to the clinic, they are talking about radioactivity in terms of millicuries, generally. They are not talking about it in terms of becquerels. But if you write a paper and try to publish a paper, you have to convert all your curies to becquerels, because the papers want the SI unit. The SI unit is becquerel, okay? But in a practical sense, people tend to talk more in millicuries, because that's, well, certainly they're smaller numbers, among other things, right? You know, if we give someone, say, 10 millicuries is a, you know, in the ballpark for, say, PET imaging or something like that, then, oh, I'm giving them 370 million becquerels. Yes, that's true, but nobody really wants to talk in terms of becquerels. So given that, you will hear both, and you will see becquerels in print, but when people talk, they're usually talking in terms of millicuries. Okay. But there's a conversion vector. Okay. Now, we are familiar with the idea in general of radioactive decay, right? In other words, a bulk of radioactive material is giving off something, and over time, it's going to change from the the individual atoms are changing from the radioactive state to the stable state and no longer giving off stuff in the stable state. And so over time, that happens. So if N is again the number of nuclei of the radioactive species, okay, then over time that's changing with respect to an exponential, and the exponential constant is a property of the material, okay, and so is therefore kind of a physical constant that's been tabulated and measured, and essentially that's the solution to the differential equation, okay. And so we can actually relate that to other quantities, but essentially that's a property, and you can look at it as the fraction that will decay per unit time. In other words, if I have fluorine 18, then every minute this fraction of the material will decay, right? And just, again, with that idea, you don't actually necessarily get to zero, you just asymptotically approach zero in terms of the conversion from unstable radioactive to stable non-radioactive. Or that's, that might be in terms of minutes, it might be in terms of days, because it's different for different materials. We tend to talk more in terms of half-life because that, again, kind of goes straight to a unit that you can process in your head pretty quickly, but lambda is related to the half-life by log 2. Okay, that's kind of demonstrated here. And so, if we talk in terms of half-life, then we're saying, okay, if this is a 6-hour half-life, I know that that 50% of the material has gone from the radioactive state to the stable state in 6 hours. And then in the next 6 hours, another 50% of what's left is going to decay, and so on and so on and so on. And of course, the whole idea, I guess, Zeno's paradox, if you start moving toward a wall and you go halfway, and then you go halfway with what's left, and halfway, you never really get there, right? Same idea here, right? We never get to, if this is true, we never actually get to zero, although because the atoms are individual units, at some point the last atom will decay. But by that time, things are far from important in the radioactivity space. And so again, different materials will follow different curves, but they're just following exponential curves. Okay, technetium 99M has a 6-hour half-life. That's a SPECT agent. Fluorine 18 is a PET agent, and it's a little under 2 hours. We always say 2 hours, but it's not quite 2 hours. And so they're going to decay at different rates, and that's going to have some implications for how you use them in imaging. It's going to have implications for radiation dose and things like that. Those are all things we're going to talk about later. But just to give a couple of examples. Generally, we say 10 half-lives. After 10 half-lives, the thing is no longer effectively radioactive, even though there's going to be some residual activity remaining after 10 half-lives. We say, enough of it's gone that you consider it non-radioactive, and therefore you can dispose of it as non-radioactive versus all the restrictions on radioactive material, right? So, for example, fluorine 18, after 20 hours, pretty much after a day, not radioactive anymore. Okay, last thing on this set, radiation dose. We're going to talk about this a lot more later, so I will just mention it here, that these are kind of physical measurements associated with radiation, that is energy deposited per unit mass. So, if you have the right measurement tool, you can actually measure those things. But that doesn't necessarily translate to the effect on tissue, right? Or the cancer risk associated with receiving a certain amount of radiation. And so that's something we're going to talk more about later in the semester when we talk about radiation biology. However, the whole idea, remember, ionizing radiation causes ionization of atoms in tissue, and which could therefore potentially react and cause biological damage is the key thing. And so how much ionization energy your tissue absorbs per unit mass is important. It's just the different tissues respond differently to that. And so in dosimetry, they have to consider those kind of things. We're not going to talk about that yet, but we will later. Okay, so that finishes the first set of slides on radiation physics. Anybody have any questions at this point? Okay, I want to get a little more into interactions in the next set, and especially the EM radiation interactions. So we talked about how particles interact with matter, and I kind of skipped this part because we have to pay a little more attention to it because it is more significant in imaging. We talked about particles, right? And I mentioned that earlier. Basically, particles interacting with matter will either generate X-rays, generate heat, or knock other electrons around, right? Which, then knocking those other electrons around will generate heat, generate X-rays, or knock more electrons around until all of the energy is dispersed. Okay. So EM radiation is going to be different because it has no mass, okay? And so we have to think about, there are going to be 4 primary ways in which EM radiation interacts with matter. So in general, okay, if an X-ray or gamma ray, remember they're physically the same, is traveling through matter, it can either do nothing, right, go all the way through to the detector and doesn't interact at all. Which some of, basically those are the things that are going to produce signal on our imaging detector if that happens. It can be that is completely deposit all of its energy in the material, okay? Or scatter. In other words, it deposits some of its energy and may or may not change its direction, okay? And so it's basically, you can think of that as maybe a partial interaction, losing some energy, but still remaining as EM radiation that's traveling, though potentially in a different direction. Okay, and so all of the 4 types, well, account for basically these last 2 possible interactions. And so each of these kind of has its own properties, and we will talk about each one. So first, Rayleigh scattering. This is like the worst thing. Thankfully, it doesn't happen much at our imaging energies because this is also called coherent scattering, classical scattering, elastic scattering. Basically, a photon comes in, changes direction, but doesn't lose any energy. And so it looks like the same thing it was before the interaction, but essentially its path gets bent. Okay, you can almost think of this as a refractory type interaction. And thankfully, this occurs more at lower energies, and so isn't hugely significant in most X-ray imaging, although potentially at low energy X-ray imaging it is. And one of the things that we rely on in imaging is we think we know where these photons came from, right? So we detect a photon on the detector. We're assuming it came directly in a path from where the X-ray source is. Well, this kind of throws that off, because these photons look exactly like the photons that were emitted in the first place, but their path has been bent. And therefore, as a result, we have much less certainty that they came directly from the source, and that makes it a little bit harder to be certain about location, which translates to blurring and loss of resolution. Okay, so so this one, yeah, these are kind of a problem. Thankfully, the probability goes down as we get to higher energies. Okay. And so we'll see more about that in a second. But basically, Rayleigh scattering, generally not too much of a problem, but in some specific cases, yes, you do have to be thinking about it. Compton is the scattering, the other type of scattering that is much more likely. And in fact, for most of imaging, this is the thing that causes the biggest problem. Inelastic or non-classical, to differentiate it from the previous one. And the idea here is the photon comes in and interacts with, say, an outer shell electron and deposits some of its energy into the electron. And when we have an electron at rest and we give it some energy, what happens? It accelerates, right? We talked about that earlier. And so it develops some velocity as a result. And since it's an outer shell, it's kind of weakly held by the atom anyway, and so it's more likely to escape. However, since all of the energy is not lost, and with the conservation of momentum, mass, etc., the resulting photon is of lower energy, because some of the energy, right, we have to balance the energy. And since it gave some energy to the electron, it has less energy left, but it's still an electromagnetic wave. And it actually has a deflection angle as a result of that, in order to conserve momentum, or, yeah, and, well, energy, momentum stuff. Okay, some hand waving there, but we have equations, so it's okay. Okay, and so this is like the most challenging thing. The basic equation for Compton scatter is this one. Okay, and so we pointed out all the different things. We have Planck's constant here, physical constant, electron rest mass, physical constant, speed of light, physical constant. And so the only thing that's variable here is the angle of scattering, and the wavelength, the change in wavelength goes basically with the scatter angle. So this is actually a pretty simple equation. One thing to keep straight is what we mean by theta, okay? And so actually, I'll draw that, because sometimes that gets just potentially a little confusing. If you have your incident photon, then it has a scatter event. Okay, so we have that scattered photon. The angle theta is the deviation from the original path. Okay, and again, you can kind of work that out logically, right? Because if theta is 0, then the cosine is 1, and this becomes 0, and so there's no difference here, effectively no scatter, right? And so it continues on the same path. So you can always kind of come back to that if you're confused by what the angle theta refers to. As theta increases, right, into a maximum angle of, let's say, pi, where it actually comes back along the same path. In other words, theta is 180 degrees, which it can be. Then this becomes -1, and this factor becomes 2, and that's basically the maximum change we could have. Okay, so it ranges from, this part ranges from 0 to 2. All right. Okay. And then, of course, that electron comes off also, although generally, for the most part, we don't, I mean, we certainly don't worry about that electron in terms of imaging, because unless we're dealing with super high energies here, that electron doesn't have enough energy to really do anything, and it quickly loses its energy to the medium anyway. Okay. Okay, so this is an illustration, but I do want to point out, sometimes you will see H nu, and this is energy, okay? Nu is a frequency, and so we'll say per second. And H has units of, well, depending on what units you use, energy times seconds. Okay, so H nu, seconds cancel out. H nu is energy, and so basically this is the same as using an E. Okay, so I don't want you to be confused like that by that. It's just that sometimes you find H nu, sometimes you find E, same thing. And now H, you know, in here, the implication is that E refers to the energy of an electron, where H nu refers to the energy of a photon, right? And that has to be the case because electrons don't have frequency. Okay, so we're kind of making that distinction, but they're both in terms of energy. Okay, again, just for purposes of Compton scattering and so forth, we won't always refer to energy of photons as H nu. We'll just kind of, sometimes we will. Okay, and so again, just as an example of kind of conserving everything, if this is the energy of the incident photon, then basically the sum of the electron energy and really the electron kinetic energy, right? Because its mass energy is still with it. The electron's kinetic energy and the remaining scattered photon have to add up to that in order to conserve everything. And so, you know, basically these equations do that. Okay. Okay. There's also an equation for the angle at which the electron has to come off, and that is basically given by this. Of course, this is part of that mass conversion, as we talked about before, and so forth. And so there is an expression here for the angle of the electron. But again, physicists will worry about the electron, but for our purposes, we aren't going to be too concerned about that guy. Just as a couple of examples, okay? So 180-degree Compton scattering. So this is the full recoil, the example I talked about before, where we come in and then essentially the remaining scattered photon bounces back in the same direction, and the electron ends up going actually off in the original direction. but the kind of properties and the way the energy gets distributed are going to be different at different energies. And so, for example, if the incoming photon is 100 keV, then the recoil photon is 72 keV and the electron gets 28 keV. Okay. But if the incoming photon is 10 MeV, again, super high energy there, we would not be using that in imaging, but a much higher percentage of the result goes into the electron. Okay, so this is not a kind of constant proportion that depends on the scattering angle. It varies with the amount of energy that's in the system to begin with. Okay. And as another example, if we were kind of scattering off at 90 degrees, and so we come in, the resulting photon comes off at a right angle to the original path, the electron, I don't know, we didn't even calculate what angle that goes off at, and it probably varies depending on the energy. Basically, that just, so that gets distributed differently, right? 83 keV in the resulting scatter. At the 10 MeV case, almost, again, almost all of the energy goes into the electron, but we're still left with 500 keV or so in the scatter. The point to see here is that the energy of the scattered photon depends on the angle, okay? And so the energy of the scattered photon could be anywhere, let's use 100 keV because that's in the X-ray range, could go anywhere from, well, 100 keV, not scattered, to the maximum, the minimum scatter event might come to 72 keV in the full recoil, and anything in between, depending on the angle, okay? And then the other thing to recognize is that in imaging, well, okay, so this guy, we have a scatter event and we're left with 72 keV photon. Well, that could scatter again, right? It's still in the material, so it is, certainly some things will have multiple scatter events. And so we could get scatter in a range anywhere from 100 keV all the way down to 0, really. So scatter tends to, range over a range of energies and a range of angles. And it's not completely isotropic as to, what angle we get. At lower energies, it tends to be more consistent, we'll say, and at higher energies it tends to favor lower scatter angles, but that doesn't really help you a whole lot. Basically, all these scattered photons coming out of your material are potentially problematic. Okay? In nuclear medicine systems, we actually detect and estimate the energy of the photon, and we can throw away some photons that were scattered on the basis of the fact that their energy is too low to have, come through without having some scatter event. Since a Compton scattered photon loses energy with each scatter event, at some point it's below a threshold and we say, oh, well, that energy is too low to have been unscattered, and so we throw it away. You can't really do that so much with X-rays, as we'll see. Photoelectric effect is also important, but this is a full absorption event. Okay, so there's not scattering going on. Basically, this is maybe inner shell electron, depends on properties of the atom, as you might expect, and drops off with higher energy, okay? It does, again, in order to balance everything out, basically, the photon coming in which is totally absorbed, but the energy has to go somewhere, and so it can certainly kick it into an electron and cause the electron to escape. Again, that's sometimes referred to as a photoelectron. If it overcomes the electron binding energy, and again, that's an ionization event. The electron is not going to go far because of the properties of particles, and so it'll interact in the medium. And so again, that's not really going to affect us, although it could potentially cause some damage, right, as an escaped ion. But of course, in order for that to happen, the energy of the incident photon has to overcome the electron's binding energy. And this is something we will see more of, but essentially, because the electron shell energies are specific physical constants for different atoms, then there actually is a discontinuity in the attenuation properties of materials, because if your incoming photon is below the electron binding energy, this can't happen, right? But once this is greater than the electron binding energy, then this is much more likely to happen. And so there are these discontinuities in terms of absorption because of that. And we'll see more about that. Basically, this only happens for materials that we introduce. Biological materials, the atoms are too light for their K edges to be significant to us. We'll talk more about that. Photoelectric effect is highly dependent on Z atomic number. And so, that interacts in various ways. But for example, we don't see that effect in tissue, but you do see it in things you introduce into tissue, like iodine or barium as contrast agents. They have K edges around in the 30 to 40 keV range, which do pop up in X-ray. And that's actually a good thing, right? You actually introduce those in order to stop more X-rays. And so photoelectric drops off pretty quickly. It does give us some distinction between bone and tissue because of the extra density of bone. Okay. But this is kind of shading the diagnostic radiology range, although there's kind of an overlap here. But basically, we do see differences. But by the time you're at 100 keV, photoelectric effect is pretty small. Okay. The final possible interaction is called pair production, and this is literally energy to mass conversion. This is creating mass out of energy. The idea is in the nucleus, the incident photon interacts with the nucleus and actually produces an electron. Here it's called a negatron, and a positron. Okay, and so basically this photon has been converted into two masses. Charge is conserved, right? One's positive, one's negative. But this can only happen if the incident energy is high enough to account for the rest masses, which are 511 keV for an electron and a positron. So basically it has to be 2 times that, and this doesn't happen at the energies we use in imaging. Okay, but it's the 4th possible interaction. Just going to be impossible at imaging energies. It seems kind of weird, energy to mass conversion, but the opposite happens in PET imaging, positron annihilation imaging, because the positron will interact with an electron, and then the two of them will annihilate each other and do a mass to energy conversion and create 2 photons out of that. More about that when we talk about PET. But basically, this is kind of the opposite of the pair production interaction. Okay, but that's not the interaction of the photon with the material. That is the reverse. Okay, the interaction of the positron with material, creating photons. Okay, so to summarize those interactions, right, Rayleigh only at the very low energy ranges that we use. Compton dominates most of the energy range that we use. Photoelectric effect is generally less than Compton, but is significant and worth paying attention to. Pair production can't happen. Okay, any questions on those ideas? Okay, this graph actually describes it pretty well. The relative contributions of the different effects at different energies. Okay, and again, the yellow range from about 30 keV in this case to about 150, but it probably should go up to 500 because of PET, right? We're working at 511 keV in PET. Still, for most of that, the the Compton curve, which is this one, is the dominant effect. Only at the very low end of the energy range, which is where we do mammography, does photoelectric become a significant piece of that. And Rayleigh, even though it's down a bit, is a bit significant there at the very low end. But as you get up into 50 keV or so, definitely Compton is the dominant effect. And again, we don't image way up here, but then pair production starts to take over when you get up to the very highest energies. Okay. And we will talk more, we will continue to talk more about linear attenuation coefficient. Basically, how does the X-ray beam get attenuated as it goes through material? Okay, but essentially, it is a combination of all those effects. The total linear attenuation coefficient, it combines the attenuation effects of all of these 4 possible things, although again, it's very energy dependent. Okay. We kind of talk about X-ray attenuation, which follows an exponential curve also, okay? And this is the same math, the same types of equations that you have for decay. That's why this is here. But the idea being that the amount transmitted is going to be less than the incident, and it depends on how much material you go through, X, and what the linear attenuation coefficient of the material is, which is usually in units of per centimeter, okay? And so we can just plug this in. We'll do more with that later, but that's the basic idea. Everything that is not transmitted is either absorbed or scattered, okay? And scattered in the sense that it doesn't make it to our detector, right? Because there would be potentially some scatter that actually comes into our detector still, but that depends on how you measure this. And of course, the idea is that the total attenuation coefficient is a function of energy. In general, in most materials, it decreases with higher energy. That is, less of the photons are stopped, unless it's one of the heavier elements, in which case it has this K-shell X-ray peak where you have a sudden transition there. And we'll talk more about those later. But basically, here's what lead looks like in this regard. And it is, of course, much more attenuating than water, although interestingly, up here at 1 MeV per unit mass, lead is less attenuating, but lead is a lot more, for the amount you have, lead is a lot more massive than water, so this is a little misleading. And of course, again, another way of illustrating the relative importance of these different interactions as a function of energy, okay, and how photoelectric drops off. Compton kind of is maximized in the middle of this range, is 150 keV, and then drops off, and then pair production becomes important. So we kind of have another way of looking at the dependence on things. Time is up, so I guess I'm going to plan to kind of stop it there. We have a little more to talk about on the attenuation coefficients and how, in general, we work with attenuation. But that's mainly what's left in this point, how we talk about attenuation of electromagnetic radiation through materials. So we'll pick up on that next time. And I will close the kind of the formal part, and if anybody wants to jump in with questions, otherwise you're free to sign off. We'll see you on Thursday.
Never decide when office hour will be.
Oh, I didn't put that on the slide, but I'll put it on the website. Fridays 1 p.m. seems to be the time at which most people are available.
Yeah.
Again, there's no time that everyone puts down as available, but I'm going to go for Friday. So I'm going to kind of reserve on my schedule Fridays at 1 p.m. And then I'm going to try to make assignments due like Monday to kind of work with that so that people can, work on the assignment some, have a chance to ask questions on Friday, and then finish the assignment after that. Okay.
No.
So yeah, I would have rather Wednesday, but Friday will be okay. We'll make it work.
All right.
All right.
Appreciate it.
Okay. We'll see ya.
All right. See you later.